Hi, in this video, I'm going to talk about a non-parametric test for ANOVA. That is, if the population does not satisfy the normal distribution, then we use non-parametric test as we did in the separate chapter, non-parametric test. So in the last chapter, that is in the non-parametric test, I discussed about how do we implement non-parametric test for the two samples. Okay, and also I briefly mentioned about the Kruskal Wallis test, which is the non-parametric test for if there are more than two samples. And I gave you one example where the ranks are not repeated, that is the data are not repeated, but we can use the Kruskal Wallis test even if the data are repeated. Okay, so I'm going to give you some examples, but it will be very brief because I covered this already in that video. So let us talk about these. So if a set of data is collected according to completely randomized design where there are more than two samples, it is possible to compare them non-parametrically for difference among the groups. Non-parametric tests are desirable if the case samples do not come from a normal population. It also works well if the population have slightly different dispersions and shapes. There are several methods for comparisons of populations using non-parametric test. Kruskal Wallis test, also called analysis of variance by ranks, is one of the best, which almost as powerful as the parametric ANOVA using the test statistic F in any situation where F test is applicable, and in fact more powerful in the cases where F test is not applicable. As in the parametric ANOVA, Kruskal Wallis tests tend to be more powerful with larger sample size, and the power is less when the sample size are not equal, especially if the large means are associated with the small sized sample. It performs well if the total data exceeds 20. If there are just two samples, the Kruskal Wallis test is equivalent to Mann-Whitney test. Note that both tests do not test whether the means or medians are different from each other, but instead address whether the sample population has different distributions. However, if the shapes are similar, then the test becomes the test of central tendency. Okay, with Kruskal Wallis test, the type 1 error is less affected with heterogeneous variance than the parametric ANOVA if the group with large variance have small sample size. So that's the note. So what are the steps for the Kruskal Wallis test? Same features in all populations, not same features in the all populations. Okay, so similar distributions and versus the non-similar distributions. Okay, all right. So the test statistic is H equals 12 over n is the total number of total number of data points divided by n times n plus 1. R1 square is basically the rank of the first sample. Square divided by n1 is the size of the first sample. R2 square is the sum of the rank of the second sample. R1 square is sum of the rank of the first sample square, and then R2 square is the sum of the rank of the second sample square over N2 is the size of the second sample, and so on. And then minus 3 times N plus 1, where Ni is the sample size of the ith sample, N is the sum of Ni's, Ri is the sum of the rank of the data in the ith sample. So this formula is used if the ranks are not repeated, okay, if none of the data are repeated. But if the data are repeated, in case of the tied ranks, the test statistic will be H sub C. That is H, this is for H sub C equals to H over C, where C is 1 minus summation TIQ minus TI over NQ minus N. What is TI though? TI is the number of ties in the ith tied rank. For example, if one number is repeated 2 times, then it will be 2Q minus 2 over NQ minus N. If another rank is repeated 3 times, then it will be 3Q minus 3. So it will be like, if there are many repeated numbers, so this T is the rank of the tied number, okay? So a number of repeated numbers. So it will be like 2Q minus 2 plus 3Q minus 3 plus 4Q minus 4. It will happen like that. If one number is repeated 2 times, another number is repeated 3 times, another number is repeated 4 times, and so on. So M is the total number of tied ranks. How many numbers are repeated? That is M. Okay. So the critical value, you can use Kruskal Wallis table there. For k is less or equals to 5, we use Kruskal Wallis H distribution table with n1 n2 degrees of freedom. For k is greater than 5, then we use chi-square test with k minus 1 degrees of freedom. Okay, if their number of group is less than or equals to 5. For if number of group is greater or equals to 5, then we use chi-square test, or we find out the p-value using chi-square test here. Okay, if the test statistic fall in the critical region, reject h sub 0, otherwise do not reject. That is for the critical value method. But if p is less than alpha, then we use we reject the null hypothesis. Let us check one example. So an entomologist is studying the vertical distribution of the fly species in deciduous forest and obtain 5 collections of flies from each of the 3 different vegetation layer: herb, shrub, and tree. The following data represent the number of flies per meter cube of foliage in 3 different layers. In the herbs, there are 14, 12.1, 9.6, 8.2, 10.2 serves. So these are the data value given. With alpha equals 0.05, test the abundance of flies are same in all 3 vegetation layers using Kruskal Wallis one-way ANOVA or one-way ANOVA by ranks. Okay, so that's the same name, Kruskal Wallis test or one-way ANOVA by ranks. So first of all, you rank the data. So these are the data points, right? So line 297, 298, 299. So these are the data points I copied. Now n is the length of h, length of s plus length of tr. So that is, I just added that. So I got n is 15. So the total sample size is 15 here. Okay. Now what is the x? So what I did in the x is I combined these 3 data into the same row. So and then I am going to rank R. Okay, so that's how we do it, right? So first of all, you combine all the data and you rank the overall data first. Okay, and then so R1 is the sum of the rank in the first sample. So what I'm doing is, you see that how does the R look like? Let us see how does the R look like. So the X look like this. Let me write down X. X is like this, and then R is like this. Okay, now so first 5 will be from sample 1. So we will add the first 5 of the ranks. So second 5 and then second 5 of the rank, add them, and third 5 and third 5 of the rank. You do that way. Okay, so now R1 is the first sum of the rank on the first 5. R2 is the sum of the rank on the second 5, and R3 is the sum of the rank on the third 5. So third sample. Okay, so what is R1? R1 is 64. That's what we got here, right? N1, N2, N3 is 5. Total N is 15. R1 is 64. What is R2? Let's find out R2. R2 is 31. And how about R3? R3 is 25, and so on. So what is H? How do I find out H? I'm just using that formula. Okay, 12 over N times N plus 1 times R1 square over length of H plus R2 square over length of, and then minus 3 times N plus 1. That's what I'm using. So let me run that H. I got H is 8.82. You see that? H is 8.82. So from Kruskal Wallis table, you use the Kruskal Wallis table, and then there is H is 0.05, and then so it is the sample size are 5, 5, 5. Okay, if you use the Kruskal Wallis test, you will get Kruskal Wallis table, you get 5.780, right? So that is the test value. So and then what is the sorry, this is the test value and this is the critical value, right? So since the test value, you see that if the test value falls in the critical region, it doesn't fall in the critical region because it falls in the critical region because we are using the right tail test. Okay, the test value falls in the critical region, right? So let me write down that. So the critical region, so let me write that critical value is value is 5.780. So the test value is 8.82, critical value is 5.780. So the test value TV falls in the critical region, hence we reject H0. We reject H0 means they do not have the same number of flies in the different vegetations. Okay, that's what we got, right guys? So let us do directly by R. That's what I prefer. Okay, so because that's what we use all the time. Okay, so you do, I just name layered equals to, I repeated herb H the number of data in H, repeated serve, and so on. So that's what I got. And then flies, I combine those. Okay. Now I don't need to do the box plot. If you want to just wonder how does the box plot look like, you see that? You see the box plot here. Okay, that's how the box plot look like. Okay, you see that? So they have almost equal, but in the herb there are many. Okay, in the herb there are many. That's why you can see that that has bigger number in the herb, right? So that you can guess that their means are not equal, or they do not follow the same distribution. Okay. All right, so because it looks like it is a right tail, this is a left tail, and it looks like I mean it's a very tight, you cannot see from here, but if you just plot the first one, you can see what tail is that. Okay, but this does not decide. It can give you just some idea, but what decides is the Kruskal test, right? Here is I am just trying to first of all, you need to arrange the data into two columns, right? So as in the one-way ANOVA. So you just put that into the all these data into one column, and then the group, the name, a herb, serve, and tree in the another column, right? So that's what I'm going to do when I do directly from R. Okay, that's the layer, and then if I'm giving another name flies. Okay, so that is basically the data. So what I'm going is I'm doing p data and data dot frame equals to fly and layer. You see that? So you are putting all those. So there are total 15 data set, right? If you do the Kruskal Wallis test, you got that the p value. So the p value here is 0.1216. So this is what we got, the p value here. Okay, so p value is less than alpha because we do not have the p value. We did the critical value method here, but anyway, p value is less than alpha. Okay, so p value less than alpha means we reject the null hypothesis. Okay, so let me write down here. So comment p is less than alpha, so we reject the null hypothesis. So this is the example if there is no tied ranks. But if there are tied ranks, okay, non-parametric test, if there are tied ranks, you see that 7.7 is repeated, another value 7.73 is also repeated, there are 7.71, 7.73 is repeated here too. Okay, there are many data repeated. So how do I do in that case? That is the thing that we want to do here. That is the next. So as we mentioned here, in case of the repeated, we will have slightly different the test value, right? So what do? Is we need to find out H over C. H is the same way that you find. C is 1 minus summation of Ti cube minus Ti, where Ti is the tie, number of tie. Okay, the number of first tie is cube minus first tie plus number of second tie cube minus second tie. So you just add them, divide by n cube minus 1. So let us do this. So I am going to do this example where there are repeated. You see that these are the data set. A researcher is studying the pH of waters from 4 ponds. The data is given below. So pond 1, pond 2, pond 3, pond 4. So they are trying to measure the pH level. Okay. So in the pond 1, they have like 7 samples. How many samples? 1, 2, 3, 4, 5, 6, 7, 8. So in the 8 samples, these are the pH values they found in the pond 1, right? And the pond 2, pond 3, pond 4. So with alpha equals 0.05, test if the pH levels are same in all 4 points using Kruskal Wallis one-way ANOVA with tied ranks. Okay, first rank all the data. So that's what I copied the data set here. P1, P2, P3, P4. K is 4, meaning number of groups is 4. So the total number of data point is 31. I just added the number of data points in each of those. And then what I'm doing is I'm putting all of them together, that is X, and then I am going to rank the X. These are the ranks, total ranks in when you combine all these in the same group and then rank them, okay, from in the increasing order. So you see that there are 7 tied ranks. There are 7 of the numbers repeated. So there are 7 tied ranks. The first one is 3.5 is repeated 2 times. 3.5 2 times. Next is 6. Rank 6 is repeated 3 times. Where is rank 6? There is 1 rank 6 here, and then there are 2 rank 6 here. So that is 3 times, and so on. That's what we got. Okay, now, so what is the null hypothesis? pH is same in all pounds, pH is not same in all 4 pounds. Okay, so what is N1, N2, N3, N4 is 8 and N3 is 7. That's what we got here, right? This one has just 7 data points, other have 8 data points. Okay, and then N equals 31, we found that already. So we want to find out the sum of the rank in the first sample. How do I do that? Is I just did that 1 through 8 and the sum of the rank, because R is the rank. Okay, R is this, so I am adding the first of these ranks there. So rank 1, rank 2, rank 3, rank 4. If you find out rank 1 is 55. You see that? Similarly, find out rank 2, rank 3, rank 4. That means the sum of the ranks there. And H is, what is the formula for H? You use that formula for the H. Okay, that's what I wrote here. H is that. H is 11.876. What do we get here? So H is 11.876. You see that? That is H value. Now M is 7, meaning that there are 7 ties, ranks are tied. Okay. Now, now you need to find out the sum of this TQ minus TT. Okay. In this case, see, the first one is repeated 2 times, so TQ minus 2. Second is repeated 3 times, plus 3Q minus 3, because there is sum. And then you continue that way, you will get 168. That's what you get. This top value is 168, and if you divide by NQ minus N, that we denote by C, the value of C is 0.9946. That's what you get. Value of C is 0.9946, and H sub C is H over C. That is the critical value for the tied rank, 11.94. 11.94. Okay. Now I want to find out the p-value. This is the right chi-square right tail chi-square test, which is 1 minus p chi-sq, HC, and then k minus 1 is the degrees of freedom. That will be HC is that value, and k minus 1 is 4 minus 1, which will be 3, right? So that's what I'm doing here. That is the p-value. So what is the p-value? P-value is basically, if you run that, you will get 0.0075. 0.0076, and there is 9. That's what 0.0076. That's what you get. And since p-value is less than alpha, we reject the null hypothesis. Okay. So what I want to do here is I want to do this directly by R. How? Just again create the 2 columns. One is for pound, I denoted by pound, and then the another is the pH level. Right? If you do the data.frame, that's what you get. Pound 1, pound 2, and then these are the pH level. These are the name of the pound. Okay. So it will be testing whether the average of the average pH of the pond 1 and pond 2 and pond 3 and pond 4 are equal or not, right? But we are doing the directly by the R, so that is Kruskal dot test. After you arrange the data, you just write Kruskal dot test. If you do that, you get the p-value is exactly same as the p-value we got, 0.007579. Or the alternative way is, instead of doing that wiggle thing, you can do least and then pond 1, pond 2, pond 3, pond 4. You will get the same result there. Hold on. We will get the same result there. Okay, 0.007579. We got almost the same value from either way, manually or by using R. Okay, so this is how we use the Kruskal Wallis test, which is the non-parametric test, to compare more than 2 populations if the population do not follow the normality. Okay guys, thank you.